Interesting concept. Okay, well, it looks like a small group today. So what can I help you all with? Samantha, you were on first. Do you have any specific questions?
I actually don't. I just thought I would join to see what I can learn from others.
Okay, Sujin, you are the next to join. You have any questions?
No, same. I don't have a good time. I just want to join.
Listen, okay.
Yeah.
All right, Ron, what about you?
You know, I'm always full of questions.
I'll take them.
Help me get an intuitive sense of the t-test. I'm reading, I'm watching the videos, and I'm reading, and I'm just not somehow understanding. And I just need an intuitive sense of what this is all about.
Yeah, absolutely. So that's a great question. What's an intuitive sense of the t-test? So I'll start first with saying that in general, in statistics, it's about comparing this group to that group. Right? So sometimes as students, or particularly if you're new to statistics, or if the data set's in an area that people aren't familiar with, they get tripped up on terminology, like what the variable name is or what the outcome means. But really what you need to look for are, what are my groups? And for the t-test, it's 2 groups. And so you can remember that because the t has 2 arms, right? So like a lowercase t has 2 arms when you draw it. Like when you make a t, it has 2 arms. So we're comparing this group to that group. And the center of the t is the overall mean. So we want to see how far apart our arms are on that little t. Does that make sense?
Yes.
Right. So if I have a systolic blood pressure, and I have a group of people with a systolic blood pressure, and I don't know anything about them, and somebody said to me, well, what's my systolic blood pressure? My best guess for them would be the mean of the systolic blood pressures that I have. That would be my best guess. But now let's say that now I'm said, oh, it's a woman, right? That provides me a little bit more information. So my question might be, do men and women have different systolic blood pressures? So that's a setup for a t-test. And what I would want to know is the average blood pressure for women different enough from the average blood pressure of men that I have 2 blood pressures instead of 1, right? So we start out with the middle, which is our mean, and then we've got our 2 arms on the t-test, and we're comparing the mean of group A and the mean of group B. So that's sort of the basics of a t-test. Let me share my screen here and we'll take a look at some t-tests. So let me see. Let's go here. Let's open. See if I can get my, oh, I've got somebody who wants to come on in. Let me admit this person. Okay, let me just pull up some data here. I should have had this open before. It's having, my computer hasn't been on all day. It's having some issues. Let's see if we can find it here. Should be it. Okay, so for the example that I gave you, and this is just a made up data set, I do in fact have my 2 variables that I was talking about. Can you see this? Okay, so I've got gender and I've got systolic blood pressures. Okay. And so the first thing that I'd want to do is do a distribution on both of my variables, gender and SBP, so that I can investigate if there's anything weird, right, about the data. There's anything strange. And it looks like I've got 43 gender values and I've got 43 SBPs, and I can see here in my rows menu that I have 43 rows, so it doesn't look like I'm missing any data. It looks like I'm 70% or 69.8% female, and I'm 30.2% male. So more females than I have males. I'm looking at a mean systolic of 114.7 These were obviously mean arterials, and with a standard deviation of 10. It doesn't look to me from the distribution. I've got a slightly high blood pressure, and maybe somebody that's feeling a little faint here with a 91. But mostly these look like a relatively healthy population. Nothing too crazy about this. So again, if we go back to that example, and just a patient comes in and says, guess my blood pressure. My guess based on this information would be that their systolic blood pressure is about 115. That would be a good guess for their systolic blood pressure. But now I want to ask the question, do men and women have different blood pressures? So that I go to my analyze menu, my fit Y by X. My systolic is my response. My gender is my X factor. And if you look over here on jump is really helpful. If you look in the fit Y by X platform window here, on the left side, it shows you what analysis you'll get. So these are your X designations, and then these are your Y designations. And so jump will tell you that if I have a nominal X, right, like gender, because it's a nominal categorical variable, it's just a name only. If I have a nominal X and a continuous Y, right, so systolic's continuous, the blue and the blue, I'm going to get what they refer to as a one-way analysis of variance. The simplest one-way ANOVA is a t-test. We just have two groups. We have male and female, and we have systolic blood pressure. So I'm going to press OK, and we get this very basic figure from jump. And there are a couple of things to point out here. Jump likes to, you can see that the distance here of females is bigger than the distance of male on the x-axis. That's just completely goes back to the fact that we have more females than males. So jump does x-axis proportional to the sample size. It's just a way to just tell you that there's more females than there are males. You can get rid of that if you guys ever want to play around, and I urge you to do that and jump on the red arrow. I can take x-axis proportional off, and then they'll go even. That's just a jumpism. You can pay no mind to the fact that it does that. But we can see here we have all of our dots, right? So we had 30 females and 13 males. You can see this gray line right here is our average overall systolic blood pressure. So that's where this 114, just approximately 115 was. This is our mean blood pressure overall for our systolic BP. So you can see our mean systolic is 114.6, and that's where this gray line is. And if you envision a lowercase t, that 114 is that center line. Okay. 114.6 is that center line. And we've got on our lowercase t with our females and our males. Now we want to know how different is our average female from our average male. And to do that, I'm just going to do a couple things first. I want to look at my means and standard deviations. I want to look at my quantiles. Those are my descriptives by gender, so that I can get an idea of what I've got here. So it looks like females are giving me a lower mean blood pressure. The question is it statistically significantly lower, right? They seem to be sort of straddling that 115. It looks like the medians are pretty similar. You can see my minimums and my maximums. My largest outlier, that 156, is a male, which is not surprising. And my lowest systolic is a female, also not surprising. So all of this is just giving me an idea of what the distributions look like. Are there any data points to be worried about? It would be odd, in my opinion, not uncommon, but odd if the highest outlier was female and the lowest one was male. That might be something to investigate. But this sort of trends with what I know about systolic blood pressure. And then I'm going to ask it for a t-test. And you can either ask it for the ANOVA pooled T, or you can ask it for the individual t-test. They're generally very similar. The difference between them is that the pooled t-test is going to use the same standard deviation. It's going to pool the standard deviations. So if we look here, we've got a standard deviation of 14 for men and just shy of 9 for women. And if we do a pooled t-test, it's going to basically average the standard deviation. It's going to assume that they're equal. If you do this t-test, it's going to assume unequal. It's just going to let them each have their own variance. Either one is fine. In most cases, they'll give you nearly identical results. So you don't need to be worried about that. I often simply just go with the pooled t-test. That's my preference, but we'll do both so we can see the difference. So here's where we get into the t-test, right? And if you remember from module 3, the standard normal, module 4, the standard normal, right? Where we center things at 0.
Right.
This is showing you that centered at 0. It's just going to use a t distribution instead of a z. It's going to show you here in the dark blue and here in the teal color where our significant values, like what's our difference. So how much is left over on the right and on the left from what our t gets us. And then what's our p-value. And so our question, remember our null hypothesis here, just pull up a new document here. Okay, so let me make my font much, much bigger so that you guys can all see this. So my null hypothesis here is SBP female equals SBP male, right? That's my null hypothesis.
Right.
114.6, I think it was, that the best estimate is the mean value. That's my null hypothesis. My alternative hypothesis is that SBP female, I don't know if I can type right, does not equal SBP male. Right, so that's my null hypothesis. Because I have means, I'm going to be using a t-test with 2 groups. And if I go back to jump here, I am going to pull out my p-value for my t-test here, which is 0.2003. Whoops. And then I'm going to compare that p-value to my alpha, which is historically what?
0.05.
Yep, 0.05, 10. Right, and so how does this p-value compare?
Much higher.
Yeah, so my p is greater than my alpha. I should really let my Microsoft Office know to not capitalize p. My p is greater than alpha, so what's my decision here?
Null hypothesis.
Yep, I'm gonna stick with the null hypothesis. There is no statistical difference. That's a key phrase, right? We have no evidence of a difference or no statistical difference between SBP for females and males.
So a kind of a dovetail question. Again, intuitive. I'm not worried about all the details, but how do you obtain alpha?
How do you know what?
Where does that come from?
So
Just an intuitive sense.
This is such a demystifying fact for people. Have you ever heard of a Fisher's exact test or R.A. Fisher? So he's a very famous statistician. We'll get into Fisher's exact test after the midterm week when we talk about chi-square tests. R.A. Fisher is a very famous statistician. And when asked about how frequently he wants to make the wrong choice, remember for the alpha level is our type 1 error. That's how often we're willing to declare HA when the null is really true. So that's how frequently we're willing to say there's a difference when there really isn't a difference. That's our alpha level. And somebody asked Fisher how frequently he would be okay making that wrong decision, saying in this case that men and women have different blood pressures when in truth they really don't. And he said about 1 out of 20. And that's 0.05.
Okay.
It could be, it's completely arbitrary. It's historic.
Yeah.
When you have really large data sets. So if you go back to the notes and you remember what the formula for a t-test is, your t-value, and this is a general, is your observed minus your expected. And then you're going to divide by the square root of your standard, of your variance, right? Or sorry, it's going to be your SD divided by your SD divided by the square root of n. So you guys don't have to remember these formulas, but it's important to sort of understand the thing. So the observed is going to be the difference between our male's BP and our female's BP. That's our observed difference, which is about 4 points. Under the null hypothesis, we expect that difference to be 0, right? So we think if this is our null hypothesis, another way to say this is that the systolic blood pressure of women minus the systolic blood pressure of men equals 0. That's another way to say the null, that the difference between them is 0. So what we would expect to see would be 0. What we observe is just our actual data, right? The larger your sample size, so this is in the, I could actually put this down here to better illustrate the experience. And again, this is not stuff that you guys have to have memorized. It's just understand sort of where it comes from. If I have really large standard deviations, this is in the denominator of the denominator, which actually puts it in the numerator. Sorry, really large n. So the larger your sample size, the larger the numerator of your t is going to be. Large t-values go with small p-values. Small p-values lead you towards the alternative hypothesis. So when you have really large sample sizes, we have a study at UAB, the Regards study. They have 42,000 people or 30,000 people in it. They often use an alpha of 0.001 because they have such a large sample size that everything's going to show up statistically significant solely because they have a really big N. The really big N is going to result in really large T statistics. That puts you over here in the T area. So if you put you here, right? And that's going to likely be significant. So they tend to use a really small alpha in the Regard studies to sort of hedge their bets for the sample size. In pilot studies, very small studies, you'll often see an alpha of 0.1, right? They have very small n, and it's a pilot study, and they're looking for evidence to go to the alternative. So they're more willing to make that error to have some evidence to move forward for a larger study. So if you go out into your research life, the UPS guys here, if you hear my dog barking, when you go out into your research life and you see, that's why it's really important to say what your alpha level is. Because if you just read the results paper and you see p-values that are 0.08 and they keep saying there's a significant difference, it's likely in their method somewhere they've told you they're using an alpha of 0.1. So alpha can fluctuate. The standard is 0.05. Large sample sizes tend to use a smaller alpha. Small sample sizes will tend to use a bigger alpha. And it's just from a famous person who said, 1 in 20.
And is that just up to the discretion of the investigator or whoever's developing the study?
Yes, but also beware. Your study doesn't exist in a vacuum. And if you decide that your p-value is going to be compared to an alpha of 0.15, people are going to pounce on you and say, wait, but so 15% of the time you're willing to declare the alternative when there's no difference. Why did you pick that? So you just need to be cognizant. We see it a lot in pilot studies. We see it a lot in early phase clinical trials because they're looking for evidence to move forward with larger studies. If you have 30,000 people in your study and you're using an alpha of 0.1, everything's going to be statistically significant. Mm-hmm. But it's not going to be meaningful. So if you look at it, I had a clinical trial a couple of years ago. We had 1,008 people, and we had an age difference in our treatment groups. But we actually looked at the ages, and it was only about an 18-month difference in the mean age in a disease that spans 30 years. So while it was statistically significantly different, no one was concerned about our age difference in one treatment versus the other one. So when you declare statistical significance, you also need to look at whether or not your statistical significance is clinically relevant. Does it mean something? Keeping in mind that larger sample sizes help you get to the alternative. And so you may end up saying, oh, we have a statistically significant difference between systolic blood pressures. And when you go look at it, it's only 1 point. Well, nobody's going to enact a protocol of a drug treatment or surgery or anything to make up for the difference of a 1 point change in systolic blood pressure. See what I'm saying?
Yeah, that makes sense.
Yeah, so it's not, and this is sort of the common fallacy about statistical interpretation, is that people often say to me, oh, you're so good at math. No, I'm not. I'm terrible at math. I'm really good at estimation. Statisticians will help you estimate things. But the decisions that you make based on the statistics have to be very holistic in terms of the context of your data. What was your setup? How strong was your design? What was your alpha? If it's statistically significant, is that difference meaningful to your population? And so those are, statistics is just a tool to help you make those decisions. Does that round it out for you, Ron, on the t-test? You're on.
Excuse me. Compared to the alternative of Z, I'm not quite sure I understand. I know you're measuring mean against mean.
Yep.
But what as opposed to what? I'm sure that's probably evident to you, but it's not to me.
Mean against mean versus what?
Versus whatever we talked about in section 4 about the alternative hypothesis and the regular hypothesis, and that's not using the t-test.
Right. So our hypotheses are independent of. So you would declare what your hypotheses are, and that will lead you to what test you're going to do. Right now, we've only looked at the t-test. That's because we have continuous outcomes. That's because we have a number. So we're comparing means. That's a t-test.
Okay.
Your research question is usually your alternative hypothesis. So when people say, I wonder if drug A is as effective as drug B. That's usually, so let's, we'll do another little here. Let's do this. Is drug A more effective than, or let's say as effective, and do two-sided, as effective as drug B, okay? That's usually our question, right? And when I can put this in numeric terms, let's say we're looking at weight loss, right? So is weight loss A equal to weight loss B? That's my sort of question, but that becomes my null hypothesis. Weight loss A is the same as weight loss B.
Okay.
Right? Is weight loss A different from weight loss B? Not different, different. These are our standard hypotheses.
Right.
Right? So I can measure weight loss in pounds. I could measure weight loss in 20% of your weight, if you're thinking about like the Biggest Loser. So I could measure it in percentage of your weight lost. I could measure it, did you lose 20% of your weight? I could measure it in the actual pounds. We could measure it in dress size. There's many ways that you could measure it. The way that you measure it, whatever your outcome is, that's going to determine the test that you have.
Okay.
So in this case, if we're looking at weight loss in terms of numbers, like pounds lost, again, that gets us to a t-test. And when we think about our null hypothesis, mathematically, I can go from weight loss A to weight loss B minus weight B equals weight B minus weight B, right? Do you remember that from algebra?
Right.
Right, so I just subtracted weight loss B from both sides, and that just gets me the difference, A, B, equals 0. That gets us onto the standard normal, right? We're comparing it to 0. We've
Right.
centered it about 0. Whee! Right? So now we just want to know how far does this difference go from our mean of 0?
Okay.
Right? What gets us to the t-test is we're going to estimate our standard deviation based on the data we have. And when you do a standard normal, which nobody does in practice, you know the standard deviation. You never know it. You always use your data to estimate it, and that's what gets us to the t-test. But otherwise, the distributions are the same shape. Our alternative here would be that the difference does not equal 0. And we want to use our data to tell us how far away does that difference have to be for us to say that we really have 2 different amounts of weight loss. And it does that based on this curve,
Okay.
what we expect to see. What we expect to see under the null hypothesis is there's no difference. We're going to use our data to tell us if what we're seeing is different from expected. Does that answer your question?
Thank you.
Okay.
I think so. It gets me on the right direction.
Okay.
I could do some more study on that.
Okay.
That's very helpful. Thank you.
All right. Who has another question?
Me, please.
Sure.
So let me check 5. Just want to clarify my understanding. You go to the subset for the cholesterol zip file 2013 from the modules, and that takes you, and then you unzip the file like you did for the other datas. Go to jump and start doing the t-test, right?
Well, you have to do some coding first. Remember, you've got to recode some of your variables.
Yeah.
So all of these came in as numeric, but they're not really numeric, right? Because gender comes in as 1s and 2s.
Yeah, yeah.
So I have to recode that. And so let me go to columns and recode. And then do you remember our males 1?
Yeah, males 1, females 2, yeah.
Which they shouldn't be because alphabetically F comes before M. But anyway, that's a whole gender bias in science. Okay, so we'll call this gender, right? And so there's my recoded gender. All right, and then we're working with cholesterol, right?
Yes.
Okay, and which variable is that?
It's numbers, so nominal.
No, where is it though? Which variable is it?
Oh, I need to check. One second.
What type variable? Is that what you're getting at?
No, what's the variable name for cholesterol?
Okay.
I'm asking because you guys just did this. So here's the laboratory variable list. If I can type. Right, so here's the cholesterol, the HDL. The total cholesterol is here, which I think that's, which one? Did we have HDL? Is that what we were looking at here?
Yes,
Okay.
It is the HDL.
Right, so HDL. So that's this one, LBD, HDD, which we have over here in our jump. So that's this one. If we do a distribution on that, which we should also do on gender to get our idea of what we've got here. I'm gonna change my histogram to show horizontal. Right, so it looks like we've got 8,291 gender responses, but we only have 7,624 of these. So we know that we've got some missing data. So the most we can have in an HDL question would be this. Okay, so we've got the data open. What was your question, Sipu?
So this was my question, just to how to just use the same data set. Am I using the right data set? And doing the same code book? That's what my question was. I haven't gone through the questions yet. I just opened my quiz and I went through that. So I was just making sure that I'll recode it and then
Yep.
using it. Is there any video you want us to follow while doing the learning check?
Nope, they're the learning check. So this process, this is the same as when we've been dealing with, if we go back to our previous data, you guys had done a lot of work with, stop it. Canvas is being a little persnickety. You guys had done a lot of work with the Burfess data set, right?
Mm-hmm.
So now you're just doing that same process.
Okay.
With the NHANES. So get your cholesterol.
Yep, I did that, yeah.
Getting the code book.
Yeah.
Right, you can link out if you want it to be a regular page. And then click on the laboratory data.
Mm-hmm.
Right, and then here's the variable list.
Oh, that's what I was not able to.
Yep, so there's the variable list. I think it says that. Yep. So click on demographics and laboratory data, and then there's various things you can do. So the laboratory link will get you the variable list from there. The demographics data is here on the left menu, so you could click on that. So part of this is also for you to learn how to use these data sets, to where to find them. And for the demographics variable list, it's here. You can also download the data file if you wanted the full data files, but you already have what you need. And so this is just not a PDF, right? So in the Burfess, we had a PDF of the code books. Here we have the links to the code books. And so you can search on these just like you could search on an Adobe. You're just searching in a web browser instead. So again, I would recommend, some of you may be using NHANES for your team projects. I would recommend that when you open the data, just spend the half an hour with it and recode your data set and then save it. So anything that needs to be changed, like gender, just look up what all the variables are. Don't just go and do the learning check, because you may end up using this data again. Plus it's good practice. But yes, that's the data. So we've got cholesterol, you've got the code book, code it, and answer the questions for Learning Check 5. It is the same process as the prior Burfess.
Okay, and another question for the discussion board. If somebody else doesn't have a question, if everyone's okay, I can go ahead and ask this.
Go ahead.
So I had a question about outcome variable and group variable.
Okay.
So I was doing a research question on the psychological effects in ICU physicians for COVID-19.
Uh-huh.
That was my, and then my outcome variable I wanted to take was sleep, like hours of sleep.
Mm-hmm.
And the other one I wanted to take is like isolation from the family. Like when they came home, they had to stay away from the family.
Right.
So I cannot measure it or I can measure how many days they were isolated, like for minutes or like days or hours. So would that class as my outcome variable?
Your outcome variable is your mental health, right? You're looking to see if mental health was impacted by isolation, right? So your isolation, very simply, would be yes, no. Did you isolate from your family, yes or no?
Okay, all right.
The outcome is the mental health variable. So in general, our outcomes are something we're going to measure. That's something that can change during the course of the study or by whatever predictor. Your predictor variables, your class variables, your group variables, those are things that are static. Okay. Right? So think about things like gender.
Male and female physicians.
Right. In most cases, depending upon what you're studying, but in most cases, you only need to ask somebody one time, are you male or female?
Yeah, because it can't change. Yeah.
Yeah, and I'm not going to predict what someone's gender is based on their blood pressure. I am, however, going to use their gender to predict their blood pressure.
Okay.
Right? So blood pressure would be our outcome. Now, there are variables that cross the line.
Mm-hmm.
Blood pressure could be a predictor if we're looking at likelihood of stroke.
Correct.
Right? So if I measure somebody's blood pressure now and then follow them, I could use my baseline blood pressure as a predictor of having a stroke or having a heart attack or, So it comes down to your questions. And I'll go back again here to our setup for our hypothesis. Right? Our groups, in terms of a t-test, those are going to be our X variables. right? We're comparing something by group. Fit Y by X. We are comparing systolic blood pressure by gender. So JUMP's very smart about that, right? If I go into my analyze fit Y by X distribution, in this case, I've got gender as my X factor, and I've got this HDL as my response. So I am fitting my HDL by gender. If I go back down here, my gender is a red histogram. That's my X. My outcome is HDL. That's my Y. That's going to get me a t-test or a one-way ANOVA. So fit Y by X. Our Ys are our outcomes. That's the thing we're trying to determine. Our X's is the thing that we know. Does that answer your question?
Yes, it did. So I'm just going to, and variable, so can I have one variable instead of variables when I'm doing in this particular assignment?
So let's look at the bigger picture. What we're working on right now are called unadjusted analyses. These are bivariate analyses. We're going to spend most of our time in this class looking at bivariate analyses up through the midterm. That's where we just do one fit Y by X, another. So we could look at gender by systolic blood pressure. We could look at the drug A versus drug B systolic blood pressure. We could look at low fat diet, high fat diet versus systolic blood pressure. And we would do 3 different analyses for that.
Okay. All right.
Standard, what's more standard, and actually I can pull up, I just finished a summary for someone this week. Let me go down here. And this is what my analytical reports look like back to people. So I've got we have very limited number of demographics. So we just had age. These are cadaver donors. So we had age and gender of the cadaver, just making sure that we don't have any differences in those, and then getting their dental type here, which is how many missing teeth they have. And then I've got all these measures. These happen to be measures of the jaws, and then these are our outcomes. And so here's all my summary statistics on those. And then I get down to, I want to compare, and all of a sudden I'm starting to get, these are all p-values. All I did for these was bivariate analysis, just like you guys are doing. And in these studies, in study 1, they were comparing one type of jaw fixation. So if somebody breaks their jaw and they put a plate in to hold the jaw focused, to hold it still while it heals, they're comparing one plate type to another plate type. So again, what is that, right? I've got 2 groups. I've got plate A and plate B, and I'm looking at the amount of force it takes to split the plate by 1 millimeter. This could be males, females versus systolic blood pressure. In this case, I've got plate A and plate B versus a force measure. The plate type is my X. The force measure is my Y. The plates are literally fixed, right? They're literally fixed, and force measure. So these are called unadjusted analyses. And then if you go down here, this is where I start getting into multiple predictors. So I'm starting to look at models for these, where I'm using several X's to predict my Y. We're going to get to that after the semester. Your data brief is solely going to be bivariate analyses. It's just going to be single X, single Y, and you're going to do 4 of those. Nicole asked, so in this discussion, we'll be writing sentences, not formulas. Yes, you'll be writing sentences. Put it into words. So if we go back to this document here, you're going to be writing words. Other questions?
And doing the t-test, I joined kind of little late. I think, I know it's a recorded thing, but in the learning check, they're asking us to calculate the t-test and the the p-values.
Yep. So let's figure out where those pieces are in JUMP. I'm going to close this out. Close this out. I'm going to go back to my test data here. And so we looked at systolic blood pressure in the prior part of the video, which you can watch. Let's actually ask the question, do we have a difference in age by gender, right? So age is my continuous variable, and we want to know, is there a difference in age between males and females? This is a question that you would often answer in, say, a clinical trial, when you're looking at demographics. So demographic-wise, do I have a difference in my ages in gender? So I'll do fit Y by X. I'll put my gender as my X and age as my Y. Let me back up here and show you what happens if you reverse them. So let me say I put my gender as my X and age, or gender as Y and age as X. If you get this figure in JUMP that says logistic at the top, you did it wrong. We don't get to logistic until the way end of the class. So if you ever see output until you learn it that says logistic, just close it out. You've mixed up your X and your Y, okay? All right, so now I'm gonna go back and do fit Y by X. My categories are my X. My continuous is my outcome. So again, nominal X, continuous Y. That's gonna get me a one-way ANOVA, which is the simplest form of an analysis of variance is a t-test, which is what we're going to do here. And again, we get just the basic output, just this basic figure, because JUMP doesn't know what test we want to do yet. So I'm going to do my quantiles and my standard means and standard deviations. So that's going to get me my summary statistics by gender, right? Because I think there's some questions about that on Learning Check 5.2, like what's the 5-number summary and what are the means and standard deviations. So that tells you here. Well, let's look at the figure first. Here's my average age. It's the gray line. It's my average age, which I can also get from doing a distribution of age, right? So my mean age is 20.6. That's this gray line right here. And for a t-test, I want to ask, is there a difference in the mean age between males and females? I know my mean age is 20.6 overall. Is there a difference between males and females in their mean age? So I've got my summary statistics here. Can go up and I'll ask for a t-test this time. I'm gonna ask for a t-test. And you get this standard output for a t-test. We'll look at the ANOVA in a second option. You get the standard output for a t-test. What you need to know are a couple of things. What's the difference between our mean ages of male and female? So you can do the math yourself, right? You can just do the subtraction. But it also gives it to you here. Just make sure you know the direction. So we're looking at a 0.39, and it looks like our females are 0.39 years older. 0.3 of a year, a third of a year, quarter of a year. They're about a couple months older, right? So that's our average, that's our difference. Here's our t-value, it's very small. Here's our p-value. We want the two-sided p-value because we're just asking, is it different than? Here's our two-sided p-value, this 0.6148. If our alpha is 0.05, is this p-value bigger or smaller than 0.05? It's 0.6. It's bigger, right? And so if our null hypothesis is that the mean age between females and males is the same, and our alternative is that they're different, and we have a large p-value, which hypothesis do we go with?
We cannot reject the null hypothesis.
Yeah, we go with the null hypothesis, right? Because our p-value here is really big. It's bigger than 0.05. So we're going to stick with the null hypothesis. And we're going to say that we don't have evidence of a difference in age between males and females. Those are the pieces. And you can see here in this little diagram of a t distribution centered at 0. Remember, because we're taking the difference between these and comparing the difference to 0. Our t is really small. It's our t-value, not our p-value. Our t-test ratio is really small. It's like minus 0.5. That's within one standard deviation, right, of a 0. It's within 1 standard deviation, so it's not that different from 0. The less of the dark blue and the teal that you see in these figures, the further out you are. Remember, things that are 2 standard deviations away, we start to think that that might be different. This is just a pictorial representation. But for the learning check, all the pieces of the information that you need to answer those are here. And if we go take a look at this learning check 5 assignments. Learning check 5. So we're like, you guys are cruising, man. We're so far into the semester already. You'll notice, I think I mentioned this earlier, but by design, we're upfronting a lot of the work so that after midterms, you guys are spending a lot of time on your data briefs so that you get the skills that you need to complete your data briefs and the second half of the semester. Okay, so it's going to ask you a couple of questions here in Learning Check 5. I'm not going to answer them for you because obviously it's not due yet. It walks you through, so here's a data brief. There's a couple of questions on a data brief that asks you to pull the data. Then it's going to start asking you about the data. It's going to ask you about recoding. What values need to be recoded on the outcome variable, right? So even though HDL is a continuous variable, there may be things that need to be recoded. So don't skip that step, right? 99 on an HDL may need to be something else. So make sure that you check the data dictionary with every variable. That's why I'm saying when you pull that data down, just sit with it for a while and recode it so that you aren't having to like go back and forth and back and forth. Just look at the data, look at the variable list, and do your recoding before you start. Look at the distributions. What is our summary that we should use? Then it's going to ask you to do what's called top coding. Top coding means that there are some people with some really extreme values, and we want to just put those all at 500. So it's going to ask you, then it's going to ask you about the shape of the distribution. Then we get into some analyses, right? Then we get into some analyses, and it's going to follow you all the way through. It's going to say to you, right, what's the test statistic? Are we going to divide alpha in half for this? What's the p-value that you get? So once you fit it all, when you recode your data and you run it, what's the p-value you get? Type that into this box, and it wants the exact p-value, which means to 4 decimal places. So don't round it. Don't round your p-values. Then it's going to ask you for the decision, which we have already walked through a couple of times here, right? Remember, large p-values are here, and small p-values will lead us to the alternative, right? So small p-values as in less than alpha lead us to the alternative. So it's going to walk you through making the decision. Then it wants your t-value, just so that you know where they are. Well, your t-value's right here. It's going to want all sorts of, so all the information that you need is encapsulated in your jump output. This is why it's really important to have your data ready so that you can actually just do the questions rather than having to go back and forth with recoding.
You suggest we keep the data like we save it?
Absolutely. So I will, every time that you recode, so I would just save as. So like what I would do here is I would save as cholesterol, and then I'll put in, let's see, I'll just say it at recode so that I know it's been recoded. So that if I ever pull the raw data set down, it doesn't overwrite all the work I've done. So I just save it as, and then every time I recode something, I'll just save it again. I won't save it as, but I'll just make sure you keep saving it. Jump's pretty good too. If you accidentally close out, it's going to ask you if you want to save stuff. The only thing that it won't do is if your computer, like, shuts off or if there's like a power surge, then you'll lose stuff. So just every time you're recoding and working with data, make sure to, it's just like a Word document. Just make sure to save it frequently.
Thank you so much. Thank you.
Sure. Other questions?
I have a separate question.
Okay.
So for our group work last week, my team is utilizing the National Survey on Drug Use and Health.
Mm-hmm.
And if you open the data set, it has a lot of information.
Yep.
Is there a way to more easily find what so like, for example, the one that we're utilizing right now, the YRBS, it's organized really well. Thing with the
yeah, so you pull down these huge data sets and you only need like 6 of the variables, right?
Yeah, and it took me a very long time to find what I was looking for.
Yep.
Is there an easier way?
There is. So remember how I said anytime you see a little red drop down arrow and jump, click on it?
Okay.
So here's a red drop down arrow. Reorder columns by name. And it will put them in alphabetical order.
Okay.
Fancy.
Okay.
It can always revert to, and then you can always go back to original order.
Okay.
If you need to. But so what you guys have done, so once you go in here and put them in by name, you can just go find them. So let's say I just, for this one, needed gender, and then I want like these others, I find them. Then just go to the tables menu and subset.
Oh, okay.
Tables subset. And make sure here you click selected columns.
Okay.
And then press OK. And now you just have a data set that has only the columns you need.
Okay, that's awesome.
So now the thing to remember about that, Samantha, the thing to be really careful about that is that you need to get all of your columns because if you forget one, you're gonna have to go back and do it again.
Oh, you can't like add on to this.
You can merge them, but that is far more complicated than I want to teach you guys how to do.
Okay.
Right? So just make sure that you've specified all the variables that you want before you do your subset. Otherwise, you'll have to go back and do it again.
Okay. One more question specific to that, the National Drug Survey. In the code book, I just feel like very confused because so much of the data says recoded. So it'll have like one question, but then it will have that same question, but it says recoded next to it. What does that?
It means that they've already done some stuff for you. So they've taken the raw variable and they've already recoded it in some manner. Race is the most common one that you'll see in these national surveys because they'll take race and ethnicity and make one variable out of it.
Oh.
And so you have to really read the code book for that. So race and ethnicity are two separate things. Race is largely, ethnicity is genetic, and right now the federal government only recognizes 2, which is Hispanic or not Hispanic. And then race is ethnicity, it's genetic, but it can also largely be cultural. Like they're different constructs. It's a very difficult conversation to have. But a lot of times what you'll see in national is that they'll say non-white, non-Hispanic, or they'll say white, non-Hispanic. So they've combined race and ethnicity. So they've already done that work for you, but you still have to recode it because they changed the numbers. So in race, white might be 7, but in the recode, white, non-Hispanic might be 1. So you just really have to read them. And then if you guys have specific questions, like point me to it and I can help you like figure it out. It will behoove you in your team projects to pick simpler variables.
Yeah, I'm kind of realizing that already. So thank you.
Yeah, it behooves you to pick simpler questions. I would love for you guys to like really delve in and ask some really in-depth questions, but you're making it harder for yourselves. Because remember that the point of this is to be able to take a data set, a code book, questions, and use statistics to answer those questions. We're not trying to cure cancer, right? We're just trying to make sure that you know how to bring data to answer the questions statistically. So it's okay if you're asking things like, are the number of days of mental health problems different between males and females? Like that's a fine question. you don't really need to like get crazy.
Thank you.
Uh-huh. Other questions for the folks that are on right now?